I used to do that a lot. I'd get my nose all
All righty, good morning, everyone. So yesterday we finished off by talking about thermal expansion. So let's do a quick example of thermal expansion and see how it actually works. And then from there, we'll move on to dilute gases. Okay. So thermal expansion, again, we have a linear expansion, which says the changes in length, an area expansion, which says the changes in area, or a volume expansion, which says the changes in volume. Each one of them are related by some sort of constant, times its additional, times the change in the temperature. So here what I have is a wall. So here's a wall. And then attached to that, I have two rods attached end to end, where each one of them starts off with an equal length of L0, which is 0.5 meters, where this piece of the metal is lead, and then this piece is aluminum. So then what we're going to do is we're going to increase the temperature such that the entire system elongates by an amount of 1 millimeter. So what I want to know in this case then is, what is the change in temperature? So how much do I have to increase the temperature by to get the system to increase its total length by 1 millimeter? So here, what's happening again is the total system is increasing by 1 millimeter, but that doesn't necessarily mean that each object increases by 1 millimeter or even a half a millimeter. And the reason for that is these two have two different coefficients of linear expansion, which means that what? The lead is going to increase length more than the aluminum is going to, which means the total amount of delta L must be equal to the sum of the length change of both of those two objects. Which basically means that the lead is going to change by some amount. So this is going to be, say, delta L of the lead. But simultaneously, the aluminum also changes by a small amount, so it's going to be delta L of the aluminum. So what we know then is that the total change, which is 1 millimeter, has to equal the sum of the two changes. So in this case, we know that the total length change must be equal to the length change of the lead plus the length change of the aluminum. Good. Now from here, we know then is that the length change is equal to the coefficients times the initial length times the change in temperature. So let's write all that down. So it's going to be equal to the coefficient of lead times the initial length of the lead times the change in temperature plus the coefficient of aluminum times the initial length of the aluminum times the change in temperature of the aluminum. In this case, we're told that the initial length of both the objects are exactly the same, which means that the initial length of the aluminum is equal to the initial length of the lead. So these two guys are the same. Also, since this is a connected system, I'm increasing the temperature of both of these two objects simultaneously, which means that the change in temperature for the lead is exactly equal to that of the change in temperature of aluminum. Which means that the only things that are different here are the two alpha values. So it's going to be alpha of the lead plus the alpha of the aluminum times the initial length times then the change in temperature. So here, I know delta L, that's 1 millimeter. I know the two alphas, I know the initial length, that's 0.5. The only thing I don't know here is the change in temperature. So let's go ahead and solve that for the change in temperature. So this says that my change in temperature then is equal to the change in length divided by the sum of the two coefficients, all times the initial length. Look at my numbers. What I find in this case then is this has a change in temperature of 38.5 Kelvin, which is the same thing as a change in temperature of 38.5 degrees Celsius. 1 degree change in Kelvin is exactly the same thing as 1 degree change in Celsius. So all that means is I have to increase the temperature from the initial temperature to the final temperature by an amount of 38.5 Kelvin or 38.5 Celsius. Either one is the same. Fine. So this is thermal expansion. Nothing too bad. That's pretty straightforward. Good. So the next thing we want to spend our time talking about today is we want to look at what's known as the equation of state of a dilute ideal gas. So what does equation of state mean? So equation of state is basically a fancy term that just means we want to determine all the elements that go into the gas, the state of it. So everything that is involved in it. So we want to look at what's known as the equation of state. an ideal and a dilute. Ideal gas. Now we're going to do this two ways. The first way we're going to look at this is what's known as the macroscopic version. Macroscopic. And then the second way we're going to look at it is look at the microscopic. So macroscopic just means big quantity. So we want to look at it from basically the outside and not worry too much about what's happening on the inside. And then the second case, we want to look at it from a more of a molecular level. So what does all the actual atoms on the inside of the gas actually do? So let's concentrate on the macroscopic state first. So let's look at the macroscopic. On the macroscopic, we have something like a container, let's say a box. And all I'm going to do is I'm going to fill this thing up with some sort of, again, dilute ideal gas. So the quantities I can measure on this thing are things like its temperature, I can measure its pressure, and I can measure the volume. These are the three macroscopic quantities I can actually measure. So by simply putting it inside of the container, I can do measurements on its pressure, I can do measurements onto its temperature, and I can do measurements onto its volume. So let's do some experiments. So basically what we're going to do is we're going to do a series of different experiments to see if we can get a relationship between all of these different quantities. So the first experiment we're going to do, experiment number one, we're going to hold the temperature equal to a constant. So in this case, we want a temperature equal to a constant. And in this case, what we want to do is we want to play with the pressure and the volume. So in this case, we're holding this guy constant. We're going to see what happens with these two things. So first things first, what I notice is that what? If I change the volume, for example, if I shrink the volume, the pressure goes up. If I increase the volume, the pressure then goes down. So ultimately what this thing says then is that what? By playing with the volume, this then has to be inversely proportional to the pressure. So this is the first thing we learned from this experiment. So again, if I increase the volume, the pressure goes down. And if I increase or if I decrease the volume, the pressure has to go up. So these two things have to be inversely proportional to each other. Now, since this guy is inversely proportional to him, what this also tells me then is that the pressure times the volume must then be equal to a constant, since these guys are completely proportional to each other. So this means that if I plotted the volume versus the pressure, we then get a line that looks something like this. Where everywhere along this line, the temperature is simply equal to a constant. This particular line, we'll talk more about this in the future, but this is what's known as an isotherm. So an isotherm is any line which then has constant temperature across. So that's what we call an isothermal process. So this is what's known as Boyle's law. Boyle's law says that the pressure and volume are inversely proportional to each other. Or more appropriately, again, the pressure times the volume, since again, if I increase the volume, the pressure goes down. This happens in such a way that this is equal to simply a constant. So this is our first experiment. Let's do our second experiment then. Our second experiment, we're now going to hold something else constant. So in this case, we're going to hold constant is the pressure. We'll look at experiment number 2. In this case, we're going to call the pressure equal to a constant. We're going to do everything at constant pressure. And again, we're going to play with the temperature and the volume. In this case, what we find is that if I increase the volume, I increase the temperature. Or if I decrease the volume, I decrease the temperature. Which simply means that if I again plotted these, say I put volume on this axis and temperature on this axis, these guys are directly proportional to each other. What I do to the one, I have to do to the other one. So there's a linear relationship between the two. So this tells me then that the volume is directly proportional to the temperature. There's a linear proportionality between the two. This is what's known as Charles' law. Charles' law says these two guys are simply directly proportional to each other. Our last experiment number 3, is now the only thing we have left to hold constant is our volume. Let's finally hold our volume constant. So in this case, what we find again is if I hold the volume constant and I now increase the pressure, if I increase the pressure, I also increase the temperature. Or if I decrease the pressure, I also decrease the temperature. So in this case, if I pull out these guys, say I put pressure on this axis and temperature on this axis, again, what I find is a nice linear straight line. So this one says that the pressure then is directly proportional to the temperature. This one is what's known as Gibbs-Sachs law. So Gibbs-Sachs law says that if you increase the pressure, you will also increase the temperature. Or if you decrease the pressure, then you decrease the temperature. So these guys are directly proportional to each other. Not too bad. Took about 300 years to do this, but that's okay. Slow progress sometimes. So if I put all these things together, what this one says then is, well, if the pressure times the volume is equal to constant, and the volume is directly proportional to the temperature, and the pressure is also simultaneously proportional to the temperature, what that also tells me then is the net result of this is that the pressure times the volume must be directly proportional to the temperature. The proportionality factor between the two then is that the pressure times the volume is equal to, write it this way, N times R times T, or N times KB times T. Either one of these is sufficient. So let's talk about what each one of these things actually are. So for this one, R here is what's known as the universal gas constant. N is what's known as the number of moles. In this case, N here, capital N, is the number of particles, where KB is what's known as Boltzmann's constant. So, give you some numbers for these things. Universal gas constant, if I remember correctly, this is equal to, right over here, R is equal to 8.31. This has units of joules per mole per Kelvin. And then KB is then equal to 1.38 times 10 to the minus 23 joules per Kelvin. So these are the different constants. So let's talk about what each one of these different things are and what settings do we actually use them. This one is roughly known as the chemistry version of the ideal gas law, which says that the pressure times volume is equal to nRT. This one, which says that the pressure times volume is equal to the number of moles times kV times T, is usually what's known as the physics version of the ideal gas law. Now, these two things are completely related to each other. And how they're related to each other is, since this is the same thing as this is the same thing as this, well, this must be equal to simply this. So let's start about each one of them. And we'll make a distinction between each one. So in this case, I have to have that the number of moles times the universal gas constant must be equal to the number of particles times NKB. But the number of moles is simply equal to the number of particles divided by what's known as Avogadro's number. So this is how we define the number of moles. The number of moles is the number of particles divided by Avogadro's number, where Avogadro's number is, anybody know what Avogadro's number is?
6.02
times 10 to the 23rd is what? Molecules per mole. So if I use that here, this now becomes the number of particles times R divided by Avogadro's number. Then it's simply equal to the number of particles times KB, which means the number of molecules is going to cancel, which means that Kb is simply equal to the universal gas constant divided by Avogadro's number. So this is the relationship between these two things. Now, physically, what's the difference? The difference is that they both talk about the energy that each particle has, but it does it in a slightly different way. So in physics, we like to think about individual particles floating around inside of a container. So in this case, our container is this entire room. So when I talk about the energy of the particles inside this room, I'm talking about the average energy that each single individual particle has. This is the physics version. So the physics version is talking about each individual atom or molecule which is inside of the gas. The chemistry version, it's the same thing, except now they're talking about the average energy of a mole worth of particles. So this is the only difference between the two. So the chemistry version is talking about the average energy that each different particle has, but not as a single individual particle, but as a mole of particles. So it groups them all together. For the physics one, we're just talking about each individual particle. This is on average how much energy it actually has. So this is what we call the ideal gas law. So the ideal gas law is either PV is equal to nRT or PV is equal to NKBT. Which one do you use? Depends on the information that you know. They tell you exactly the same information. Again, this is just the energy per mole. This is the energy per molecule. So if I told you the total number of particles, you would use this one. Or if I told you the total number of moles, you would simply use this one. Whichever one that you use, it doesn't really matter. It just depends on the information in which it is that you know. But again, these two guys are related to each other by this formula here. So again, Boltzmann's constant is simply equal to the universal gas constant divided by Avogadro's number. Okay? Not too bad. So this is the ideal gas law. So the ideal gas law simply is the state of the gas in macroscopic terms, where the macroscopic quantities we can measure are simply its pressure, its volume, and its temperature. This tells you everything that you need to know about this particular ideal dilute gas. So let's use this and let's do a couple examples. Let's see how this thing actually works. So my first example says we have an ideal gas which is at an initial temperature, so let's say initial, which is equal to 20 degrees Celsius, and has an initial pressure, initial, which is equal to 1.5 times 10 to the 5th pascals. And we put this in some sort of container, which has an initial volume, which is equal to 1 liter. So in this case, I want to determine the number of moles in the gas. So for part A, I want to know how many moles are contained within inside of this gas in this container. The second part then says I have a piston which pushes, or the gas pushes against the piston, expanding the gas to twice of its volume, while its pressure falls to atmospheric pressure. So I want to find then what is the new temperature. So let's say here is my container initially. So what's happening is I have a piston which is set here. All the gas is inside of this container. So this is the initial volume. So all my gas is. Then for part B, this piston then is going to go all the way to the other side of the container. So now all the particles have moved around. So now it has a final volume, which is equal to twice the initial volume. So what I want to know now is if the pressure, the final pressure falls to 1 atmosphere, then what is the final temperature? So in this case, the volume is expanding, the pressure is going down. So I want to know what happens to then the temperature. What is my final temperature in this case? Good. So let's do part A first. So part A, we want to know simply what are the total number of moles. Now, one thing to point out about the ideal gas law is the ideal gas law only works when my system is either in equilibrium or quasi-equilibrium, which means that if my system is changing rapidly, I can't use the ideal gas law anymore. So what has to be true is that it has to go from some initial state to some final states where those two initial and final states are in equilibrium, or at least quasi-equilibrium, they're close to equilibrium. How it goes from state 1 to state 2, or in this case my initial state to my final states, depending on the details on how that changes, the ideal gas law may not be satisfied as it goes from one state to another state. If it's not, what you have to use is something that's very equivalent to what's known as quantum field theory. That's well beyond this class. So we're not going to do that. So the only way we can use the ideal gas law is if it goes from some initial state, which is in equilibrium, to some other final state, which is in equilibrium. But as long as the system is in equilibrium, the ideal gas law must be satisfied. Which means that initially the system is at equilibrium, which means all of these quantities then have to satisfy my ideal gas law. So to find the number of moles, what we can say then is that, well, the initial pressure times the initial volume must be equal to the number of moles times the universal gas constant times the initial temperature. So as long as this is in quasi-equilibrium, this has to be true. So for here, I can then say, well, my number of moles then is just equal to the initial pressure times the initial volume divided by the universal gas constant times that initial temperature. Now here, the problem was nice enough to give us this in pascals. But from there, since we're working in SI units, this has to be in Kelvin and this has to be in meters cubed. So we do have to do a conversion. Now, one thing to pay attention to when it comes to temperature, if I had an initial temperature to a final temperature ratio and I simply left it in Celsius to find that ratio, as opposed to first converting it to Kelvin and then finding that ratio, note that that is wrong. And the reason that is wrong is because, unlike most of the things we talked about in this class, temperature is an additive transformation, not a multiplicative transformation. Which means that if I took something like 20 degrees Celsius divided by 99 degrees Celsius, that ratio is different than what it should be, which is 293.15 divided by 273.15 plus 99. Because it's an additive instead of a multiplicative transformation between the two temperature scales, that then changes the size of the ratio. So just be careful of this when you actually do temperatures. So in the ideal gas law, when I try to do a ratio between temperatures, no, I have to put it into Kelvin first because that changes the size of the ratio. And we'll do that in just a second. So anyways, point here is first we have to put this into Kelvin, put this guy in then to meters cubed. Once we do that, plug in our numbers. We find in this case then is that the number of moles is equal to 0.0616. So this is the total number of moles I have within inside of my gas. Let's talk about part B. Part B then says, what happens now is I go from this original equilibrium state. I have some expansion in here. I don't really know exactly how that expansion works because it doesn't tell me, but what I do know is it goes from an equilibrium state to an equilibrium state. Which means that when it's in its final equilibrium state, the ideal gas law must also be satisfied. So by the time it gets to this final state, what has to be true is that the final pressure times the final volume must be equal to the number of moles times the universal gas constant times the final temperature. Now, what I would usually do from here is I would say, well, if this is true and this is true, what happens if I divide these two? Just an easier way to do it. So instead of working with this, I'm going to turn this thing into a ratio. That way I don't need to know the number of moles, and I also don't have to play around with the universal gas constant. So if I simply divide this thing by the initial state, what happens then is that these guys are going to go away, which then leaves me with a ratio. So in this case, what must be true is that the final pressure times the final volume divided by the initial pressure times the initial volume must be equal to the final temperature divided by the initial temperature. So in this case, my final temperature then is simply equal to the initial temperature times then the final pressure times the final volume divided by the initial pressure times then the initial volume. So in this case, what do I know? I know that the final volume is simply equal to twice of the initial volume. So then I can rewrite this as the initial temperature, final pressure divided by the initial pressure, times twice the initial volume divided by the initial volume. So the initial volumes are going to go away. I don't care about that. So this thing is then simply equal to twice the initial temperature times then the ratio of the two pressures. Okay? Remember the final pressure is atmospheric pressure. Remember atmospheric pressure is 1.01 times 10 to the 5th pascals. So in this case we would use that. Look at my numbers. What I find in this case then is my final temperature works out to be 27.01 degrees Celsius after I convert back by subtracting 273. So this is my final temperature. Okay. Let's do another example. Next example says we're walking on the beach. We find an old bottle which has a note in it. We think it's a treasure map. We get all excited, we want to find the treasure. So we decide that we want to open up the bottle. But we don't have a cork, right? Well, we don't have a bottle opener to open a cork. But we get too excited because we think maybe the treasure is on that beach that we're walking on, so we don't want to go back to our hotel room or house or wherever it is that we in to find a bottle opener. So we decide to open the bottle in a different way. Not by smashing it on the ground, even though that would open a bottle, but that would also probably shred the note that's in there, maybe the treasure map, and we don't want to do that. So we're going to have a different way that we're actually going to do it. So what's a good way that we can do it? What's a good way we can open up the bottle? Increasing its temperature, right? So what we're going to do then is we're going to take the bottle. Here's my bottle. And as Debbie said, what we're going to do is we're basically just going to build a fire. Right? And we're going to hold the bottle over top of the fire to then increase the temperature inside of the bottle. And then what does that do for us, Debbie? It's going to expand it and increase the pressure. And as it increases the pressure, that'll put enough pressure onto the cork that the cork is going to go popping off. Right. So this is what we want to do. So let's first build our fire. Let's throw our fire. Some nice blue in the middle. That's nice hot temperature. There's our fire. Good. So in this case, we want to build the fire so that the cork is going to pop out. So let's say initially, inside of the bottle, we have a temperature initially which is equal to 30 degrees Celsius. So this is the initial temperature of the bottle. Inside, the initial pressure is equal to atmospheric pressure. So this is equal to 1 atm. And let's put some sizes on the cork. So let's say the cork here has a cross-sectional area A, which is equal to 2.3 centimeters squared. Good. Now again, we're going to put this over the fire. What happens then is the final temperature that this thing reaches to, the final is equal to 99 degrees Celsius. So from here, what I want to know then is, for part A, what's the final pressure inside of the bottle, if this is true? And then finally, for part B, what I want to know is what force of friction held the cork in place just before the cork popped out. So I want to know what is the frictional force. We're going to take it to the moment just before the cork popped out. So how much friction force was actually happening on this guy? Everybody's okay? So we're going to do the same thing as before. So what's going to happen is this thing initially starts off in an equilibrium state. So we know that the ideal gas law has to be satisfied. When we raise it up to 99 degrees, it's also going to finish in an equilibrium state, which means that the ideal gas law must also be satisfied. So in this case, what I have to have is that the initial pressure times the initial volume must be equal to the number of moles times R times the initial temperature. But at the end, I also have to have the final pressure times the final volume must also be equal to the number of moles times the final temperature. Now, in this case, I never told you what the number of moles were, so we're just going to do the same thing we just did, take a ratio between these two things. So let's go ahead and divide these guys. So if I divide them, again, what this says is that my initial volume times my initial pressure divided by my final volume times my final pressure must be equal to the initial temperature divided by the final temperature. I simply take in your ratio of these two guys. Good. Let's solve this for the final temperature. So what this says then is that my final temperature is equal to my initial temperature times the ratio of my final pressure to times my final volume divided by my initial pressure times my initial volume. Actually, no, I know the temperature. Oh, we'll leave it this way. Let's divide that over here. I already know the temperature. I need the pressure. But anyway, we'll leave it like this for now. Now, we're looking for this. We know this. We know this. We know this. The only things we don't know now are the volume. So, for the volume, we can do one of two things. So, either we can look up exactly what the beta is for this guy, right? So remember the volume coefficients of expansion, find out exactly how much this guy expanded, or we can say, make an approximation, and how does the final volume of the bottle compare to the initial volume of the bottle? It's about the same, right? So even if I heated up the bottle, it's going to expand, but it's going to expand minutely compared to the actual volume of the bottle originally, which means that the final volume is going to be roughly the same size as the initial volume, roughly. So in this case, if we make that assumption that the final volume is roughly the same size as the initial volume, what will happen in this case then is these two volumes will simply cancel. So from here, this thing finally tells me that the final pressure is equal to the initial pressure times then the ratio of the final temperature to the initial temperature. Here, we know the initial pressure is 1 atm. We know the final temperature. We know the initial temperature. Plug in our values. What we find in this case then is that our final pressure works out to be 1.23 atmosphere. This is harder. Okay with this?
On the last one, you
Sure.
left it in Pascal. And then this one, you
Right, so here, as long as I'm looking for this, since it's a multiplicative relationship between pascals and ATMs, I could just leave it in ATMs.
so as long as they're the same.
Well, as long as it's not an additive change. Yeah. So remember that 1 atmosphere is equal to 1.01 times 10 to the 5th pascals. So since this is a multiplicative change, I can just leave this in terms of pascals or in ATMs because it's not going to change anything. But the temperature, again, because it's an additive change, I do have to change that into Kelvin first, and then find the ratio in terms of Kelvin, and then multiply by that 1 atmosphere. So in this case, as long as it's pressure or volume or any of those, I can do it in the same units as which it is that I'm given, because it won't actually change anything. The only one I do necessarily have to change is the temperature. Again, because it's additive, change the size of the ratio. Was okay? So last thing is, we want to determine what is the friction force. So let's draw a free body diagram. So here's my free body diagram. So let's say here's my cork. So let's think about a cork. So on the cork, on the inside, I have what? A force trying to push it out in this direction, which is the force from inside of the bottle. So this is, we call that my final force, or let's say my interior force. It's called force E. But since my bottle is an atmosphere, what that means then is I have air on the outside also trying to push the bottle's cork inward, which means that there's also a force pushing in this direction, which is my atmospheric force, or my atmospheric pressure. But what I also know is that the force on the inside is greater than the force on the outside, so I'm trying to push in this direction, which means that my static friction force must be in this direction. If it wants to move that way, which means static friction must be in the opposite direction. Good. Let's call this our x direction. So from here, we can say then is, well, this is just before it actually pops off, so this has to be a static system, which means the sum of the forces must be equal to 0. So from here, we can say the sum of the forces in the x direction must be equal to 0. So from here, I have the force on the interior minus the static friction force minus the force from the atmospheric pressure pushing in must all then be equal to 0. Oh, good. Okay? So from here, this says then that my static friction must be equal to simply the difference between these two forces. But from here, I didn't tell you the forces, which you know are the pressures. So from here, we can say then is that, well, the interior force is then going to be the force on the inside, which is what we call the final force, times the cross-sectional area, minus then the atmospheric force, which was the initial pressure, times then that same cross-sectional area. So here we're going to make the assumption that a cork that has the same cross-sectional area here as it does here, uniform cross-sectional area through. So this A is the same thing as this A. So finally, what this tells me is that my static friction must be equal to the final pressure minus the initial pressure all times the cross-sectional area. Now, the other thing we know is that the final temperature is related to the initial temperature by the ratio of the two temperatures. So the final pressure is the same thing as the initial pressure times the ratio of the temperature. So we put that in. So this is going to be T final over the initial minus the T0 all times A, which finally then gives me that the ratio of the temperatures minus 1 times the initial pressure times the cross-sectional area is all equal to the static friction force. Okay? What's up, Carson?
Why can't you use the final pressure you found in part A?
I could, but again, just in case I made a mistake. Like when I find the final pressure and I forgot to put this into Kelvin, I forgot to put this into Kelvin, then I can make up for that remedy later. So, then I just like algebra. So. Try to teach you guys beloved algebra too. At least as much as I can. Great. Thermodynamics, what we find in this case then is that the static friction becomes 5.24 times 10 to the minus 5 newtons. So this is my static friction. Pretty small. But no, if you were confident with your final pressure, you could just use that there. Myself, I just always look to go back to the things that were given to me instead of using something I actually calculated. Also, that helps with rounding and all that good stuff as well. So. Was okay? So not too bad. So there's applications of our ideal gas law. So yeah, the ideal gas law in this stage is the equation of states or a statement of how the gas is actually behaving on a macroscopic level. So yeah, the only things we can measure on a macroscopic level are its pressure, its volume, and its temperature. That's it. So now we want to switch gears and look at the equation of state from the microscopic. Talk about what's actually going on. So what's the microscopic viewpoint of the ideal gas law? So what happens in this case? So let's look at the microscopic. So the microscopic, let's say here's our big container. Again, the microscopic, what we care about are all the individual atoms and what they're doing on the inside. Now, the key part here is that two things. Number one, it's dilute. And the second thing is that it's an ideal gas. So what do these two things mean? Well, we talked about this before. Ideal gas simply means that the only interaction between the particles is gravitational. So this means that it has to be a gravitational interaction between the particles. Which means that if I had one particle here, another particle here, the only interaction that these two have with each other is simply a gravitational force pulling these guys slightly towards each other. But since this thing has a ridiculously small mass, this one has a ridiculously small mass, and it's dilute, meaning that these things are going to be spatially separated pretty well, this force is going to be almost non-existent. almost approximately a zero force. So dilute means that there's not a lot of gas molecules being here. So this is what dilute means. So not many particles. Now, the other thing not many particles means is that if these guys are zipping around, so let's say this one has a velocity going in this direction, so let's call this velocity v. This one has a velocity, say, going in this direction, velocity v. As these guys are bouncing around inside of this box, the likelihood of a collision between these two particles is also approximately zero. Because this one's going to be bouncing around all over the place, this one's going to be bouncing around all over the place. The likelihood of a collision between these two guys is going to be roughly zero. We're not going to get many collisions. So this is our other big thing about not many particles. So likelihood of collision is approximately zero. So basically, what's going to happen then is that this single particle, let's call my particle here, is going to randomly go like this, bounce off the wall, go across the room, and knowing who was ever in this room, bounce off the wall, come back, and then bounce off the wall again. And it's going to keep doing it. Okay? So basically what happens then is what? As this particle goes, bounces off the wall, what does it do to the wall?
There's a force on it.
It feels a force, right? So what I want to know then is what on average is the average force that this wall feels from this thing colliding with it. Now we're going to make an assumption. Our assumption here is that our collisions will be elastic collisions. So what's going to happen then is this particle is going to fly, hit this wall here, and then bounce off in this direction. So that this angle here is exactly the same as this angle, and so my particle is here, the velocity that it has in this direction is exactly the same as the velocity in that direction, anti-glass. Because, what? The mass of the wall is infinite compared to the mass of the particle. So in this case, we know that this guy simply is going to bounce off in the opposite direction, which means that the change in momentum in this direction and the y direction, I have no change in momentum. But in the x direction, what's happening then is I'm having a change in momentum, which is twice of the initial momentum. Okay. So in this case, what I know is that the change in momentum of the particle is only equal to the x portion of the change in momentum, which is simply going to be equal to twice of the initial momentum of the particle. Cool. My initial momentum of the particle is simply equal to its mass times its x portion of the velocity. It's only the x portion of the momentum. Newton's second law then says that the average force acting on the particle then is equal to the change in momentum of the particle divided by the change in time, which means that this is simply equal to twice the momentum divided by the time. Now, what I also know is that this is the average momentum on the particle. What's true about the average force on the wall?
I should be the same.
Just in opposite direction, right? So this is also equal to the magnitude of the force on the wall. Good. Now what's the time? Well, the time is, again, since this thing doesn't actually collide with anything else, the time between successive collisions then is simply going to be the time it takes for this thing to go across the room and back. Okay? So this is going to be the time between successive collisions. So my time then, with zero acceleration, from our second kinematic equation says, well, the distance we're traveling is twice the length of the room. So this is then equal to the initial velocity, which is only the x portion of the velocity times the time, which means the time between successive collisions is simply equal to twice the length of the room divided by the velocity, which is moving. So let's put that in here. So this thing finally becomes, the 2's are going to cancel, so it's going to be m times vx squared divided by the length of the room. But this is only the force by one particle. So if I wanted to know the total force on the wall, due to all the particles in the room, if this is the average force from one particle, then the average force from each particle will be exactly the same, which means the total force then on the wall is going to be simply equal to the sum over all of these average forces of the wall. But since all of these guys are the same, I'm simply going to add n number of these if there's n number of molecules. So this is going to be equal to n number, n times the force on the wall. Because at the end of the day, this is going to be equal to n times the x squared divided by the length. Well, we also know that the force per unit area is simply equal to the pressure. So the pressure then on the wall is going to be equal to then the force on the wall divided by the cross-sectional area A. So this is going to be equal to then n times m times bx squared divided by a times L. But what's a times L? So it's area times length. Volume. So the same thing then as n m bx squared divided by the volume. Now, last thing to note is that this thing here looks very specifically like kinetic energy. Remember, kinetic energy is 1/2 mv squared. So here, if I have an mv squared, I should be thinking that this thing looks pretty similar to kinetic energy. But kinetic energy deals with the entire velocity, where this thing is dealing with only the x portion of the velocity. So what I want to do then is I want to talk about, well, how does the average velocity in the x direction compares to the average velocity in the y direction compares to the average velocity in the z direction? So if I was looking at a box, which is just sitting there with air kind of moving around, if there's no breeze blowing through my box, as in this room, what then is the average velocity in this direction versus this direction versus this direction? It's the same. So the average velocity, as long as I don't have a breeze, the average velocity each one has in a different direction has to be exactly the same. Which means then that what? The velocity squared must be equal then to the x component of the velocity squared plus the y component of the velocity squared plus the z component of the velocity squared. But since each one of these is identically the same, this is simply equal then to 3 times the x component of the velocity squared. Which means that I can rewrite this then as 1/3 of n times m times the total velocity squared divided by the volume. Now, I know 1/2 mv squared is the same thing as the kinetic energy. So if I multiply top and bottom of this by 2, I can now convert this into the kinetic energy. So this thing finally says then is that this is 2/3 the number of particles divided by the volume times then the average kinetic energy. This is then the pressure. So what this thing says is that pressure is actually related directly to the average kinetic energy. Now, since this is an ideal gas law, what I can do is I can actually rewrite the pressure times the volume in terms of the number of particles times kV times the temperature. I'll skip that for a little bit, but basically what I'll write down is our final result, which is what we talked about yesterday, that the temperature is directly related to the kinetic energy. So in this case, what I find is that the average kinetic energy is actually equal to 3/2 kV times. This is the other big result we get out of this. So let's discuss this a little bit. The two things I really get out of this is what? That the pressure of the box that I measure is simply related to how often are the particles colliding with the wall. The more they collide with the wall, i.e. the greater the amount of kinetic energy they have, the more they'll collide with the wall because they're more energetic, they're more moving, they're more colliding with it more often, that increases the pressure. But simultaneously, kinetic energy is simply related to the temperature of this object, which means that kinetic energy and temperature are the same thing. What we talked about, I think, 2 days ago. Temperature then is actually a measure of kinetic energy, which is a measure of how fast the particles are actually moving. The faster they move, the higher the temperature becomes. So if I put these two things together, this gives me identically the same ideal gas law that we had before. So this is the microscopic version. So what we perceive as pressure is nothing more than how many times are these particles slamming into this wall. This is then pressure. Temperature is simply a measure of the kinetic energy at which these particles have. This is what temperature actually is. So this is the microscopic version. We'll do a little bit more with this tomorrow. The other thing is tomorrow, what I want you to do, don't come here initially. So over this way, everybody know where the kiosk is here? Around the corner on the way to the health professions building. You go out that door and you go straight down the side wall there. There's a loading dock there. There's a trash can there. I want you guys to meet me there. The reason we're going to do that is we're going to blow up the garbage can. It's going to be great. We're going to do that with liquid nitrogen. It's going to be fantastic. All it has to do with this. And I'll explain when we actually get there. So we'll do that first thing, and then after that, we'll come up here. We'll do an example using this. I'll talk about this a little bit more. And damn it, I'm going to get back your exams today because I forgot to do that for 3 days in a row now. So, okay. I give that to you. I'm sorry. Do something right here. Oh, then. So, you get your exam. I'll see you guys tomorrow. Welcome. Not bring anything back, but things I do consider. Garrett. Person. All right, I'll see you ready tomorrow. Again, let's meet outside by the loading dock. Blow some garbage cans.
Dude, don't diss the proportion.